Hey, welcome to the Explainer. Today, we're going to crack the code on a fundamental algorithm that's literally everywhere, from searching a contact in your phone to finding a product on Amazon. It's called binary search. It's a really simple idea with some staggering power, and you're about to see exactly why.
Okay, so let's kick things off with a little puzzle. Imagine I hand you a massive million-page phone book, and I tell you to find one specific name. How would you do it? I mean, you could start at page 1 and just start flipping, right? But that could take forever. But what if I told you there's a way to slash that phone book in half with every single guess you make?
You know that page-by-page slog? That's what we call a linear search. And yeah, it works, but man, for big piles of data, it's just painfully slow and inefficient. The smarter way, binary search, works by cutting the problem in half, again and again. It is fast, it is powerful, and honestly, it's just really elegant.
So, what's the secret sauce here? Well, at the very heart of binary search is this powerful strategy you see all over computer science. It's called divide and conquer. Instead of trying to tackle some huge problem all at once, you just systematically break it down into smaller, much more manageable chunks.
Okay, now this is super important. Before we go any further, there is one golden rule for binary search, and you absolutely cannot break it. The data has to be sorted. Just think about that phone book again. The whole reason it works is that all the names are in alphabetical order. That sorting is what lets us make these smart guesses and just eliminate huge sections of data all at once.
And the logic behind it? It's so simple it's beautiful. You just jump straight to the middle of your list. You ask one simple question. Is the thing I'm looking for bigger or smaller than this middle item? And based on that answer, you instantly get to throw away half the data. Then you just do the exact same thing on the half that's left over.
All right, enough talk. Theory's one thing, but seeing this bad boy in action is where it really clicks. Let's walk through an example.
Okay, check this out. We've got our sorted list of numbers, and our mission, should we choose to accept it, is to find the number 42. So, to keep track of where we're looking, we'll use two little pointers. We'll put one, let's call it low, at the very start of the list, and another one, high, at the very end. Everything in between is our search zone.
First move, we don't start at the beginning. Now, we jump right into the middle of our search area. In this case, the middle spot is index 8, which holds the number 36. That's our first guess.
And here comes the magic question. We look at our target, 42. Is it bigger or smaller than the number we just landed on, 36? Well, that's easy, right? 42 is bigger. And because, and this is the key, because we know the list is sorted, that simple answer is incredibly powerful. It means 42 cannot be anywhere in the first half of this list. Gone. Just like that. With one comparison, we've thrown out half our problem. So what do? We just slide our low pointer up to where the middle was, and we get ready to go again on this much smaller list.
And from here, we just rinse and repeat. It's the same exact process. In our new, smaller zone, the middle value is 62. Our target, 42, is smaller, so we toss out the entire right half. The next middle is 47, still too high, so we get rid of that right half too. And on our fourth check, the middle element is 42, and bam, there it is. We found it, a list of 15 items, and it only took us 4 guesses.
Okay, that's great when the number is actually there. But what about when it's not? What if we were looking for, say, the number 30?
Well, the process is exactly the same. We keep cutting and we keep narrowing our search, but eventually you're going to see something interesting happen. Our little search space gets so tiny that our low pointer actually moves past the high pointer. And that's the signal. That's the algorithm basically shouting, hey, I've looked everywhere, it's not here.
You see how we just walked through that? The really cool thing is, we can take that whole intuitive idea and boil it down to a few simple steps a computer can follow perfectly every single time.
And this right here? This is basically the engine of the whole thing. It's just a loop that keeps running as long as low is less than or equal to high. As long as we still have a valid place to look. Inside that loop, it does the same 3 things over and over. Find the middle, check for a match, and if it's not a match, toss out the half you don't need by moving one of the pointers. That's literally all there is to it.
So why do we care so much about this? Why is this algorithm such a big deal in computer science? Well, the answer is all about its speed. And trust me, it's mind-blowingly fast.
Just take a look at these numbers. This is where it gets crazy. For 16 items, you need at most 4 guesses. Okay. For over 1,000 items, only 10 guesses. Now get this. For a list with 1 billion items, it would take you at most about 30 guesses. That's not just fast, that's almost unbelievable. This incredible efficiency has a name. We call it logarithmic time complexity, and you'll often see it written as O of log n. Now, logarithm might sound scary, but all it really means is we're asking a simple question. How many times can you chop something in half before you get down to just one piece? That's it, and that's why it's pretty much the gold standard for a fast algorithm.
So you have your best case scenario, which we call O1. That's when you get super lucky and the very first middle element you check is the one you're looking for. One and done. But even the worst case, where you have to keep searching till the very end, is still that ridiculously fast O log n.
And if you're still not convinced, this chart says it all. To find something in a million items, a linear search, that's the one-by-one method, could take you a million steps. But binary search, worst case scenario, about 20. I mean, it's not even a fair fight. They're playing completely different sports.
So when you boil it all down, what's the big lesson from binary search? It's that the secret isn't just about finding the right thing. It's about being incredibly smart and efficient about getting rid of all the wrong things. The fastest way to find that needle in a haystack is to just keep throwing out half the hay. And that kind of leaves us with one final big idea to chew on. This whole divide and conquer strategy, it's more than just a search algorithm. It's a powerful way to think. So think about it. What other giant, complex problems, maybe in your work, or even just in your life, could be solved way faster if you just figured out a way to cut them in half?